Hi, let's continue our journey through the land of flip flops and let's look at this slightly more complicated flip flop. This flip flop that is on the screen here is called a JK flip flop, and the complexity basically arises from the fact that you use three input AND gates here at both the inputs, and you take the Q and the Q bar outputs and feed it on to the inputs. Now let's see how what difference does this make. One of the things you would notice is that this part of the flip flop here is this is just an SR latch, right? Made of NOR gates. And so I've just written the truth table of the SR latch here so that we can refer to it as we walk along the functioning of the JK flip flop. Is that okay? Okay, so let's start. So the first thing that we can do is we can look at the case when the clock is 0. Now, if the clock is 0, what is the output of this AND gate? The output of this AND gate is going to be 0, right? Because one of the inputs here is 0. And what does an AND function do? If any one of the inputs is 0, the output is going to be 0. So this becomes, the output here becomes simply equal to 0. And similarly, the output of the second AND gate, which is this one, is also 0. Maybe it will be helpful if we number our AND gates, right? Let's call it 1 and let's call it 2. Now, if that is true, if the inputs here are 0 and 0, then the outputs Q and Q bar, if you look at this truth table, for R and S equal to 0, 0, you get the output Q and Q bar. Okay, so then we can fill up this truth table. So if clock is 0, it doesn't matter what J and K are, the output is simply going to be Q and Q bar. Let's also give names. This is R input and this is the S input, right? In the SR latch. So let's just write it for our reference there. Okay. So now let's go to the next phase where we assume that a clock is 1. Okay. So let me just erase this input, and let me say that the clock has become 1 now. Okay, if the clock has become 1, now j and k can take 4 different values, and let's start with the values j equal to 0 and k equal to 0. Now if j and k are both equal to 0, what is the output of the AND gate 1? It is still 0, right? Because k is 0, so this is going to remain 0. What happens to the output of the AND gate 2? Again, this is also 0, and therefore the output is going to be q bar still. So clock is 1 and j and k are 0, 0, and we still get q and q bar. Okay, now let's go into the more difficult aspects of the flip-flop. Okay, so let's try to make k equal to 1. So let's make k equal to 1. Now if k becomes 1 and j is still 0, what's the output of AND 2, the AND gate number 2? It's still 0 because j is 0, so this is going to be 0. But the output of the AND gate 1 depends. We don't know what it is going to be, and it depends on what. Now k is 1, clock is 1, but what about q? So depending on what q is, the output here is going to change, right? So let's say q is equal to 0. So let's just assume that q is 0. If q is 0, then the output here is going to be 0. The input to AND gate 1 is going to be 0, and this is going to be 0, right? And you have R and S equal to 0, 0. So this is already 0 and this is also 0. So the state is going to be maintained. So Q will be equal to 0 and Q bar will be equal to 1. So it's like we are maintaining the state, right? So Q bar is equal to 1, because let's assume that the outputs have different values. They don't take the same values. Now, we started off last time, what we said was that uh, we assumed that q is 0, and then we found that if q is 0, q remains 0. What happens if q is actually 1? If this is 1, the input here is going to be 1. So the input to this AND gate is 1, 1, 1. So the output of the AND gate is going to be 1, right? And so now you have R equal to 1 and S equal to 0. So if you have R equal to 1 and S equal to 0, you can look up this truth table and you can see that Q is going to be equal to 0 and Q bar is going to become equal to 1. Okay, so the output then, so if we start off by assuming that our q equal to 1, by the end of the operation, by the end of you going through the gate, this q is again going to become 0, and this is going to become equal to 1. So the output in the case when j is equal to 0 and k equal to 1, the outputs q and q bar are going to be 0, 1. Okay, whatever the previous state was. So let's write that in our truth table. So clock is 1 and we have j equal to 0, k equal to 1. So q and q bar are going to be 0 and 1. Now the next state is where j becomes 1 and k becomes 0 and the clock is still 1. So let's try to look at what happens in this case. Okay, I'm just going to try to erase all these red and green markings that I've made, and we'll make it anew again because we want to look at it freshly. Let's leave the clock alone and let me just redraw the connections here. Okay, so that's okay, and what we have is we are saying that we are going to have j equal to 1 and k equal to 0. Now if k is equal to 0, what is the output of AND gate 1? This AND gate, since one of the inputs is 0, this is R is always going to be 0. So this is going to be 0. So that is good. Now let's look at S. Now the S or the output of AND gate 2 depends on what Q bar is, right? So let's start off by assuming that Q bar is 0. If Q bar is 0, Q is going to be equal to 1. So if Q bar is 0, what happens to the inputs of AND gate 2? So this becomes 0 as well, and therefore S becomes 0, and R and S 0, 0 is the memory state, so the same state is going to be maintained. So the state is going to be 1, 0, and that state is going to be maintained in the next condition as well, next cycle as well. Okay, now what happens if Q bar is not 1 but it is 0? So let's say it's not 0 but it's 1, so we start with 1, so then Q is 0. So if Q bar is 1, the input here is 1, so then S is 1, and if S is 1, let's look at the state where R is 0 and S is 1. You get Q equal to 1 and Q bar equal to 0. So you end up with Q equal to 1, Q bar equal to 0. So in whatever state we are in to start off with, your Q and Q bar are going to return to 1 and 0 when J is 1 and K is 0. Is that okay? So we have Q equal to 1, this is 0. Okay, now the last condition is when J and K are 1 and 1 and the clock is 1 as well. So what happens in this case? So I've just stopped the erased the markings in the previous case, and now let's try k equal to 1 and j equal to 1. Now the outputs of both gate 1 and gate 2 depend on what q and q bar are going to be, right? So let's say we start off with q equal to 0 and q bar equal to 1. What happens then? So if q is equal to 0, then the input to AND gate is 0 here, so R becomes 0 here. And if q bar is 1, we have 1 here, and therefore S becomes equal to 1. Now when r equal to 0 and s equal to 1, what do we have? 0, 1. So we have q equal to 1 and q bar equal to 0, right? So our outputs. So let's just maybe make a small table uh, here. So we said we started off by with the state 0, 1, and what we have when you start off with the state 0, 1 is r equal to 0 and s equal to 1, which results in q equal to 1 and q bar equal to 0. So what we have is q equal to 1 and q bar equal to 0. Okay. Now let's start with the opposite output. So let's assume that q was 1 and q bar was 0. So what happens now? So then the input here becomes 1 and this input becomes 0. So this s becomes 0 and this r becomes 1. And in that case, you have r equal to 1 and s equal to 0, which is this state. Then q and q bar are 0 and 1. Okay. So what did we start off with? We started off with q equal to 1 and q bar equal to 0, and we ended up with 0, 1. So you can see that what's happening when j and k is equal to 1. Whatever the state is here, that state we are going into the opposite state, right? If q was 0, it becomes 1. If it was 1, see, if it was 0, it becomes 1. If it was 1, it becomes 0. And similarly for q bar also, it also goes into the opposite state. So if we want to write this in the truth table, what we can say is q becomes equal to q bar and q bar becomes equal to q. Okay, so in the JK flip-flop, J and K can both take the values 0, 0 and 1, 1. But if 0, 0 is considered to be the the memory state, 1, 1 is kind of the inverse memory state, right? It remembers what was previously, but it just inverts the whatever was stored in the JK flip-flop. Okay, so that's how a JK flip-flop works.